So we're going to get started with this next problem. It's problem number 654. It's called maximum binary tree, and it has an acceptance rate of 70.9%. It's rated as a medium, so let's get into it. So it says, given an integer with no duplicates, given an integer array with no duplicates, a maximum tree building on this array is defined as following. The root is the maximum number in the array. The left subtree is the maximum tree constructed from the left part subarray divided by the maximum number. So the left subtree is the maximum tree constructed from the left part. Okay, the left part of the subarray divided by the maximum number. Okay. And then the right subtree is the same thing, but for the right. Construct the maximum tree by the given array and output the root node of this tree. Construct the maximum tree given by the given array and output the root node of this tree. So what is the maximum tree? A maximum tree is that. Okay. So it seems like we're going to be, if we run through this example that we were given, with the input being 3, 2, 1, 6, 0, 5. Let's see how they did it. So it says that the root is the maximum number in the array. So right now the maximum number in this array would be 6. So 6 becomes the root. And then we have a left subarray and we have a right subarray. And then from there we want to basically branch out its children. So on the left side, it's 6's left child would be the maximum number in this subarray, which is 3. And then we're left with a subarray on the left, which is nothing, it's empty, and then a subarray on the right, which is 2 and 1. So continuing down this path, if we continued, the greater child on the right side is 2, so we get a 2. The greater child the greater the greater element on the right side of 3, the right subarray of 3 is 2, and then we're left with nothing on the left and one element on the right. So this just becomes, since it's on the right side, it becomes a right child, it seems like, and then we do the same thing for this right side here. So between 0 and 5, we're on 6's right child. The greater element is 5, and then we're left with nothing on the right, and we're left with this 0 on the left. So 0 becomes the left child because it's on the left. And it seems like that's the same thing they did. That was their output. So let's see what they're using. So they're using this tree node class. It seems like we can do this recursively. Whenever I think of trees, I kind of jump to a recursive solution because I've seen many problems done recursively that involve trees. So it doesn't matter if there's any negatives. We're just looking for the maximum. Let's go for a brute force solution, or I don't know if it's the best solution, but a brute force solution is we'll have so starting with a fresh array, we have 3, 2, 1, 6, 0, 5. We can have a left and right boundary, so left, right. Those would be parameters taken in to our function as function arguments. And then in that, we have to scan for the biggest element, and then set that as the value. So here we do 6. Let's go over the edge cases first, I guess. What are the edge cases, or base cases for our recursive algorithm to stop? So one thing I definitely see is if the right pointer is less than or equal, or less than the left. So saying that the left is greater than right would be a breakpoint. And then from there, Are there any other things we have to worry about so we don't get like an array out of bounds index, array out of bounds like exception? Other than that, I'm not really seeing much. It doesn't matter if we have negative numbers. This is just an integer array. So it seems like we got a pretty good understanding of this problem. Let's try to, so we said we'd use a recursive function to get this done, and we're using this tree node class to create the tree, the maximum tree. The way we're doing it kind of reminds me of quicksort, where you pick a pivot point, which you can have as your middle element, and then you like find all the elements to the left that are great or less than, and then all the elements to the right are going to be greater than, and then you kind of continue on the left and right subarrays, and then do that recursively. The only difference here would be that instead of picking the middle as the pivot, you pick the greatest element as the pivot. So it seems like for every call to the function, we're going through the subarray to find the greatest element, and by doing that, it seems like our time complexity would be big O of n squared, I believe, and our space complexity would be big O of n, because we're doing n such calls. Let's see. Well, I know for sure it's big O of n squared time. We'll figure out the space when we evaluate it. Let's go ahead and plan this. So first step is find the max within left and right bound, the left and right boundaries. The next thing we did was so after finding that, we have to add it to our tree. Add to tree. And depending on if it's the left, okay, so recursively it would be this add to tree, but for the first time it seems like we're going to have to manually do that because our tree will be empty and we don't know if it's going to be the left side or the right side. So once we've added it to the tree, then we want to repeat 1 and 2 for left and right subarrays. Great, so what I'm a little confused on right now is how we get the start to work. Like, once this is in the process of doing this this thing here, it's pretty self-explanatory what we have to do, but what I'm confused on is the first iteration. So let's just go through an example, I guess. I'm gonna write some code here alongside. I'm going to create a private helper function. Will it return a tree node or no? Let's have it as a void function because it doesn't need to return anything, I believe. So private tree node, or private void, let's just call it helper for now. It'll take in the integer array nums. It'll take in left and right. After that, it can take in a tree node root. And the purpose of doing that is so we can actually add to our tree. So we have our base condition if left is greater than right, we want to return. I guess we could have, if we have our return type as tree node, we just return null, and then as we're going on, but then at the very end it'll always return null. Okay, so let's keep that as a void. So if left is greater than right, we have that. Let's have a find max function. Index of max is going to equal, let's say find max index, and we're going to pass in this nums. And let's pretend we have this function written out for right now, and we'll go ahead and go back and implement it later. So it'll return an int. It's going to be the index of the max element between, we actually have to pass in this left and right boundary because we want to check within the bounds, not the whole array. So we'll pass in here left and right. So once we have the index of the max, we want to go ahead and create that tree node. So we're going to have tree node. This is going to be the root element for now. Sorry, tree node root is going to equal a new tree node, and we're going to pass this nums, the element that's at this index of max. Okay, so I think I'm seeing where we're going to go with this. So basically we want root dot right to equal this helper, and we're going to have to change this from a void to another to return a tree node, but basically you'll pass in nums, you'll pass in index of max plus 1, you'll pass, so that'll be the left, the right will be, remains the right, and you'll pass in, so I don't think we actually need this right now, it seems like we don't need this. And then the same thing goes for the left, where we have root.left is equal to left and then index of max minus 1. So when we have this, we'd have to return tree node. If left is greater than right, that's true, we want to return null. Otherwise, you get the max index. You get the tree node root. And then at the very end, you just want to return root, I believe. So I think I'm confusing myself out a little here. I just want to run through this problem once. And then we basically call it by saying this, return this with nums 0 and then nums.length minus 1. So let's just go through this code really quickly, like by hand, with a very small array. So let's do 1, 5, or 1, 7, 5, 2. It's a pretty spread array. So our expected output should be 7, 5, and 2. And our left should just be 1. So that would be our maximum tree. That's the expected output. When we actually run through our code, taking this code here, so we have left as 0 and right as 3. And we'll pass in nums, we pass in left and right. So left is not greater than right, so we won't return null. The index of the max, let's assume that our function's already written. it'll give us this 7, or sorry, 1, IOM, let's call it that. IOM is equal to 1. So it creates this new tree node, and so 7 will be there. And then it says root.write, our new what'll be our new recursive call will be to using this write subarray. So we're passing in nums, we're passing in index of max plus 1, so we're passing in 2 to 3. And now here on this side, we're doing the same thing. So left is not greater than right. Our index of max is going to equal find the max index. So between 2 and 3, what is the greatest number? So that should be 2. So it returns 2, IOM is equal to 2. And then it says root is equal to this new tree node and of this. So basically we create this tree node 5, and then we say root.write is equal to this helper using nums, index of max plus 1, so 3, and then write, which is 3. We also haven't done any of the root.left stuff because we're going recursively into this helper function. So I'm just going down like as if the computer would do it. So now we're getting this helper. Left is not greater than right. Our index of max will be whatever find max index returns, which in this case it's only one element. So it should be this 2. So it returns index 3. So IOM is equal to 3. And that element is basically 2. So once we have this 2, it goes ahead and says root.write is equal to helper. So we create symbolically, we're going to say root.write is equal to helper, nums, and index of max plus 1, so 4, and then write, which is 3. And in this case, helper actually returns null because our left is greater than our right, and so we return null here. This is basically null. We go into root.left, or we try to create a root.left with the left, which is 3. So here we have, in this stack call, we have 3, and right will be 2 because we're doing index of max minus 1. So again, we return null because left is greater than or equal to right. So we return this 2, and finally, we go back up this stack call and we return this subtree here. So it just gets 2 and null, but we don't need to draw that out. So I actually really like this problem so far because sometimes I have troubles visualizing how to solve tree problems with recursion. And I know like anything you can do recursively, you can also do iteratively using like a stack. But it really helps to get your mind thinking recursively from what I've heard, and it stretches your brain in such a way that you're exposed to new problems and you have a different mindset of thinking, I guess. But anyway, let's continue. So now we're back up to this index of max is equal to 2. We did the right. Now we're going to do the left. So with this left, we're going to have root.left equal to helper. We're going to pass in nums. We're going to pass in this 2. And we're going to pass in our right will be 2 because index of this max minus 1 is 2. Or index of this right minus 1 is 2. So 2 and 2 comes in here, and we'll have the same case where we just return the max element will be 2, and the element at 2 is 5. So did I do that right? Okay, we have this 2 and 3. And once we have this 2 and 3, we did the root.right. We're coming to this root.left. And we have equals to helper nums index of max minus 1. So why is that we have this going on now? We did our we're over here. So we had 5. We did the right, which is 2. Now we're on the left. So pass in left, which is 2, and index of max minus 1, which is now 2. It should be, does that mean our left should be greater than or equal to right? But then in that case, this won't ever run in return 2. Or is it the case where we have to, when we're doing the left subarray, we have to do index of max minus 2, but that doesn't make sense either. Oh, I see. So index of max will be, the index of max right now is 2, so sorry, yeah, I confused myself. Right now left is equal to 2 and right is equal to 3, but where our index of max is equal to 2. So we're basically saying that we're going to take, on this side, we're going to do the left, which is 2, and then index of max minus 1, which is 1. So left is greater than right, and we return null. So this is a null. And we finish with this, so we return basically the root, which is this, but that also has these links with it. So we're returning this tree up to here. So we have 5, and we won't draw out the null, but we'll take this 2. And so now we're back up to this part of our stack, our recursive calls. So left is equal to 3, left is equal to 0, right is equal to 3, and index of max is equal to 1. So we already did root.right is equal to whatever. Now we're going to do root.left is equal to helper, and we pass in all these arguments. So when we come this way, our arguments for this helper first will be, so we're passing in index of max, we're passing in left, which is 0, and we're passing in index of max minus 1, which is 1 minus 1, which is 0. So on this side, we come in here, and into helper, left is not greater than right. We find the max index, which is 0, and we create a tree node, which will be whatever is at index 0, which in this case was 1. And so this is our tree node, and we say root.right with index of max plus 1 and right, which is 0, so it returns null. It's going to be a null. And we do the same thing with this root.left, and we pass in 0 and -1, and in this case, it's going to return null because left is greater than right. And finally, we return this root node. We return root, so up to here. Basically, we return this 1 here, and along with that comes these nulls, but I'm not going to draw them out. And this would be finally what we return. So we just return this root, this 7, because we're back up to this stack call. And with that, we end up returning the maximum binary tree. And so you can see that 7152 was what we wanted, 7152. That's exactly what we wanted. Let's go ahead and implement this find max index function. So for this, basically, we're just going to start off creating a max value. So int max is equal to whatever is at num's left. And then we're going to iterate through I is equal to left plus 1. I is less than right. We're going to do less than or equal to right because we have the case where left and right can be equal. So just want to make sure. If we had 0 and 0, yeah, okay. If we had 0 and 1, this would only do one iteration of our loop because we're setting max equal to whatever is here, and then we're doing left plus 1 starting here, but if we did I is less than right, we'd never actually end up going in this loop here. So we're going to do less than or equal to right, and then we're going to say I plus plus. At the end of every loop, we want to increment I, and we're going to say that if nums at this I is greater than max, we will return, max is going to equal nums I. One thing came into my mind right now is that will there be any duplicated numbers? So can there be like duplicated maximums? Okay, it explicitly said no duplicates. So I think I mentioned that when I was trying to understand the problem, that there will be no duplicates, there will be no negatives. That's definitely one of the big things you want to check for. Because if that was the case, we might have to modify our algorithm in such a way that it satisfies the requirements. So after we check for the max, we just return max. Sorry. We're going to say max is equal to, because this returns the max element, not the max index. So we'll say max is equal to left, and then we'll say if nums at I is greater than nums at this index max, then max is going to equal to I. And by doing this, instead of returning the element, we're actually returning the index of the max element. So just going through that again real quick. Sorry about that. Max is going to equal left. I is equal to left plus 1. If the element at I is greater than max, then we'll set max equal to I. Makes sense. And then we'll return max. Cool. So it seems like shouldn't be a problem running this. Let's go ahead and try to run it. We got a compile error. Okay. So, okay, so the expected answer actually has the nulls, which is good. Error method, construct maximum binary tree and cannot be applied to given types. What does that mean? So, let's see, read that again. Line 12, we're returning this construct maximum. Oh, sorry, I called this function instead of this helper. So that should fix the problem. And we got the same result, 635 null, 2, 0, null, null, 1. And it's correct. Let's try to submit it. And it was accepted. So reviewing this, we have O of n space. I was actually thinking about that because when we went through this, when we were trying to work this problem out, the 7152, we could see that at no point in time was there like duplicated work done. Like for example, in the Fibonacci numbers, we weren't doing extra work that could have already been calculated. So we have O of n space. Or would it be O of log n? We're going through the height. Well, actually, in this case, no, because it's an array, not a balanced binary tree. So it'd be big O of n space, and big O of n squared time. Because every time we go, we have to look at the max element, and that has to be done linearly because we're not storing the max. That definitely seems like a bottleneck, finding the max every time. And I'm wondering if we could have that saved. But that wouldn't be... So it was accepted. I feel like if there was a problem with our time or space complexity, it would... I know like HackerRank kind of times out. Let's take a look at some of the accepted solutions. Divided versus partitioned. Oh, no, this is just feedback. So this guy did it recursively as well. If this num is equal to null, return null. Makes sense. Started with this build function. If starts greater than end, we return null. The index of the max is going to equal start. He did this. Basically, I modularized. I had another helper function doing this portion, but it's the same thing. He had it there. And then he said roots equal to this, and it's exactly the same way that I did it, recursively. This guy says it's the same as quicksort, which would be n log n. I think we talked about that in video before. It would be kind of n log n if the max element was at the middle of the array every single time, but that's not guaranteed. Or at least that's what I think. I could be wrong. The idea is to use divide and conquer each time we create a node root for the maximum value in the range. Yeah, makes sense. Then we split it left range and right range, which are the left subtree and right subtree of this maximum node root. So we got the max index again. Same thing in C++. Seems like the solutions that are here are this in a similar way to the way we did it. So I want to leave it at that, and excited to do the next video. Cool. See you guys later.